In this part of the Neurocomputers and Deep Learning course related to training feedforward neural networks, you will learn backpropagation algorithm for multi-layer perceptron. Now assume that another layer of neurons is connected to the input side of the output layer. Therefore, we have the input, hidden, and output layers. In order to discriminate between the elements of the hidden and output layers, we will use the subscripts L and O respectively. For this layer, we are using the subscript L, and for the output layer, we are using the subscript O. Furthermore, we will use H as the index on the hidden layer elements, while still using index J for the input layer and I for the output layer respectively. We are considering Uj at the input layer and XHL, the hidden layer, and XIO at the output layer. In such a network, the output value of ith neuron of output layer can be written as the output of the ith neuron at output layer when input UK is applied is output function applied on the activation WIO. This is the weight vector of the neuron I at output layer transpose multiplied by the output vector in the previous layer. So if we return to figure, the output of this neuron is the output function applied on the activation, which is the weight vector of this neuron. Here also the threshold values are considered. Transpose of the weight vector multiplied by the output of this layer, because the output of this layer is input to the neurons at the output layer. Here, X, LK being the vector of output values at hidden layer that is connected as input to the output layer. The value of the H'd element in XLK, this is the output of the hidden layer neurons, is determined by the equation XHLK is equal to the output function for the neurons at the L layer on the activation WHL. This is the weight vector of the neuron HL at the hidden layer L transpose UK. This is the input vector applied at the input layer. Notice that this weight transpose UK is equal to summation J from 1 up to n. This is the inner product, so we have W, J, HL multiplied by UJ when the input K is applied. Then the partial derivative of the total error EK is equal to, here notice that the total error is summation of the error at each output square IO. This is the index at the output layer from 1 up to m. And here we have 1 over 2. And instead of the error at the ith output, we can write the desired output minus actual output. And if we write the partial derivative with respect to W, J, H, L. Notice that we are trying to find out the partial derivative of the total error at the output with respect to a weight between input layer and a neuron in the hidden layer. In such a network, the output value of ith neuron of output layer can be written as the output of the ith neuron at output layer when input UK is applied is output function applied on the activation. This is the weight vector of the neuron I at output layer transpose multiplied by the output vector in the previous layer. Here, XLK being the vector of output values at hidden layer that is connected as input to the output layer. So if we return to figure, the output of this neuron is the output function applied on the activation, which is the transpose of the weight vector. Here also the threshold values are considered, multiplied by the output of this layer, because the output of this layer is input to the neurons at the output layer. The value of the edged element in XLK, this is the output of the hidden layer neuron, is determined by the equation XHLK is equal to the output function for the neurons at the L layer on the activation WHL. This is the weight vector of the neuron HL at the hidden layer L transpose UK. This is the input vector applied at the input layer. Notice that this weight transpose UK is equal to summation J from 1 up to n. This is the inner product, so we have WJ HL multiplied by UJ when the input UK is applied. The partial derivative of the output of a neuron IO. The output of neuron IO, neuron at the output layer, with respect to hidden layer weight WJHL, this is the connection from input UJ to hidden layer neuron XHL, can be determined by applying the chain rule. The partial derivative of this output with respect to this connection weight can be written as partial derivative of this output with respect to output of the hidden neuron. So partial derivative XIOK with respect to output of the neuron HL multiplied by the partial derivative of the output of the neuron HL with respect to connection weight WJHL. So we are writing chain rule and consider this output. In this equation, we have output function f applied on the weight vector of this neuron and outputs at the previous layer. So we are considering the term where we have XHL. Instead of this term in the chain rule, we can write the derivative of the output function multiplied by the connection weight given here. So we have WHLIO, this connection weight. And for the second part, we have the partial derivative of this output XHL with respect to this connection with WJHL. The output of the neuron HL, here we have the output function. Because of that, we have the derivative of the output function. Then we have the weight vector of this neuron transpose multiplied by the input vector. And this is the summation J from 1 to n WJHL UJK. So if we are considering the term WJHL, we will have UJK here. So we derived what is the partial derivative of the output of a neuron at the output layer with respect to a connection weight between the input layer, input J, and a neuron in the hidden layer. Previously, we have derived what is the partial derivative of this output with respect to this connection. However, we are trying to find out what is the partial derivative of the total error And here notice that we have a summation and square of the error at the ith output. Because of that, when we take the partial derivative, there will be 2 multiplied by 1 over 2. They cancel each other. Then we have the error epsilon I. Okay, this is the error at this output neuron. And furthermore, inside here, if we try to find out what is the partial derivative of this error with respect to this connection weight, if we expand the error, we have such a term here. Here we have output XIO K. So a minus comes here. And because of this summation, we have IO from 1 up to M. So this is the partial derivative of the total error when UK is applied at input with respect to connection weight WJHL. By using the definition of the error term at the output, the previous formula can be reformulated as the partial derivative of the total error with respect to this connection weight is equal to summation IO from 1 up to M minus, and here we have error term, and then the rest is same as in the previous formula derived. If we define the error term for the neuron H at the hidden layer L as the derivative of the output function of this neuron at the activation of that neuron when input UK is applied, and here we have summation, the output IO from 1 up to M, the error term there, WHL, connection weight from the neuron HL to neuron IO. So here we have these in the summation. Then if you write the error term for the hidden neuron, this can be simplified as the partial derivative of the total error with respect to this connection weight written as the error term of the hidden neuron HL multiplied by the J component of the input. Therefore, the weight update rule for the hidden layer can be written simply as WJHL at t plus 1 is equal to its previous value, and this is learning rate multiplied by the partial derivative of the total error with respect to connection weight to this connection weight. And we have minus here to go in the negative direction of the gradient and also multiplied by the learning rate. This can be reformulated in analogy with the weight update rule of the output layer as WJHL at t plus 1 is equal to its value at time t plus learning rate, the error term for the hidden neuron H at layer L when input K is applied multiplied by the input Uj. This is the weight update formula, just we constant. Here we have input J. However, if we have several layers, instead of Uj, we will have the output of the J neuron in the previous layer. Instead of each J here, we will have J of the layer L-1. Then the rest is the same. So Wj of the layer L-1 HL, the connection weight between these two neurons at t plus 1 is its previous value plus learning rate and the error term at the hidden neuron HL and the jth neuron output at the previous layer, where L and L-1 are used to denote any hidden layer and its previous layer respectively. Furthermore, this was the error term. This error term may be generalized for the networks having several hidden layers. Again, instead of HL, we are going to use J L-1. So the error term of a neuron J at the previous layer is written as the derivative of the output function of the neuron at layer L-1 applied at the activation of that neuron, and there is a summation HL. This is the neuron in the next layer from 1 up to NL. This is the number of neurons in the layer L. And then instead of this error term, we will have HLK and multiplied by WJ L-1 and HL, where NL is the number of neurons at layer L. So the error term of a neuron J in the previous layer can be calculated as summation of the error terms at the next layer multiplied by the connection weight between that neuron in the next layer and our neuron in the previous layer. Here there is a summation for all neurons in the next layer and also the derivative of the output function of our neuron at its activation. We can summarize the backpropagation algorithm for multi-layer network as follows. Step 0, initialize weights to small random values. All these weights are initialized to small random values. Step 1, apply a sample. Apply to the input a sample vector UK having desired output vector YK. Step 2 is corresponding to the forward phase, starting from the first hidden layer and propagating towards the output layer. We are starting from first layer and we are propagating towards the output layer. 2-1, calculate the activation values for the units at layer L as 2-1-1. If the previous layer L-1 is the input layer, then the activation of the neuron H at layer L when the input UK is applied is equal to summation J from 0. 0 is corresponding to the input 0, which has value 1, so that connection is corresponding to the threshold. J is from 0 up to N. W, J, the connection from that input neuron to our neuron HL multiplied by the J component of the input UK. 2-1-2, if L-1 is a hidden layer instead of input layer, in that case, the activation of the neuron H at layer L and input K is applied is equal to J of the layer L-1 starting from 0 up to number of neurons in that layer. We are multiplying the connection weight of the J neuron of that previous layer with our neuron H at the current layer multiplied by the output of the J neuron at the previous layer when input UK is applied. We are considering the output of the neuron J at the previous layer. 2, calculate the output values for the units at layer L as X, the output of the neuron H at layer L when the input UK is applied is equal to output function applied on the activation of that neuron calculated in the previous step, in which use index IO instead of HR if it is an output layer. Neuron isn't a hidden layer but the output layer, then we are using IO instead of HR.
Step 3.
Output errors. Calculate the error terms at the output layer. Error term for the neurons at the output layer when the input UK is applied is equal to desired output for that output component minus the actual output of that neuron multiplied by the derivative of the output function at the activation value of that neuron multiplied by the derivative of the output function of that neuron calculated at activation of that neuron. IO, the backward phase. Propagate error backward from the output layer to the input layer through each layer L using the error term. The error term for the neuron H at the layer L when the input UK is applied is equal to the derivative of the output function of that neuron calculated at the activation of that neuron and summation of the error terms for the neuron I in the next layer, starting from 1 up to number of neurons in the next layer, and this error term is multiplied by the connection weight from our neuron HL to the neuron I in the next layer, in which use IO instead of IL plus 1 if the next layer is an output layer. Weight update. Update weights according to the formula. The connection weight of the neuron J of the layer L-1 to the neuron H at the layer L. This is the next layer at time t plus 1 is equal to the value of that connection at step t plus the learning rate multiplied by the error term of the neuron HL multiplied by the output of the neuron J in the previous layer. The desired output. Repeat steps from 1 up to 6 until the stop criterion is satisfied, which may be chosen as the mean of the total error. Mean of the total error for each input UK is equal to, this is 1/2 summation on each output neuron, the desired output and actual output when that input is applied, and we are finding what is the mean value is sufficiently small.